Greetings, welcome back to the channel. Today I'm going to share a visualization technique for quite a complicated inequality problem with constraint using Wolfram Language. So the first one is the original problem posted on the Chinese math problem discussion forum. They use quite a clever algebraic techniques to break down. It is very clever, but the issue with that problem is usually it does not work if we break the symmetry, so like the second one, and it does not show any information about the target function, if how the value of target function changes with respect to the change of xyz. So I think this is the great moment that I'm going to show you a very powerful Wolfram visualization functions to tackle this type of issue. First, let's use built-in functions, unmaximize and unminimize to find the global maximum and the global minimum for these functions. And here is the constraint. The next step is to call the function spherical plot 3D. And the first argument is 1, because sphere everywhere the radius is 1. It's independent of theta and phi. And here, theta works as a latitude and phi works as longitude. The information of the target function is parameterized with the color function. This function calls color data with temperature map as its customized color gradient. So here, blue means the lowest value, and the red means the largest value or the hottest point. You can see that the lowest value is minus 0.16 and highest value is 0.125. In the function, you can see the first part is temperature map, the name of the color gradient. And the second argument is the minimum value to the maximum value, which gives the range of this temperature map. Now let's visualize this function. Okay, so this is the graph or the temperature map of the function x squared minus yz times y squared minus xzx times z squared minus yx on the sphere. You can see these blue region are the lowest value, the coldest place. The highest temperature place is on the equator, sort of on this equator. And I use this transparent plane to indicate where you can take all the highest value on this surface. The other way to visualize the same thing is to convert xyz back into theta phi Pac-Man plane. These theta phi choose the same range as those in the spherical plot 3D. And instead of using the spherical plot 3D as a plot function, we use plot 3D directly, because at this time, the theta phi plane is simply same thing as the flat Euclidean plane we see all the time with xyz. And now we have the visualization of the same target function on different plane, and we keep the temperature map and the contours to indicate how these values are changed from the maximum value to the minimum value. There are 6 lowest points on this plot, and we can compare it with the points on original spherical plot. And the maximum is not just a single point, but it's a band, which corresponds to the sort of equator, the red equator on the original spherical plot. And they do match perfectly. We can also find the contour of the maximum value on theta phi plane using the information from the equators in the spherical plane, because the crossing plane is simply x plus y plus z equal to 0. And if we replace the x, y, z with the cosine theta and the sine phi, just like what we have in the parameterization plane, we can simply using counterplot to visualize this ridge using the counterplot function on theta phi plane. So this line exactly matches the curve on the ridge, as we can see here. Let's just conclude the first problem and move to the second one. In this case, I'm going to do exactly the same thing using the same routines to check out the maximum and the minimum value first. As I modify the target, the minimum value and maximum value actually changed. And this time the value is computed much faster than the first one, because in this case, the minimum and maximum are at exactly a point instead of a surface or a contour line that satisfy the same condition. And we use almost the same syntax. So spherical plot 3D, 1, because 1 is a constant, it means it's a sphere. And what we change here is, in the color map, even though the syntax is the same, but the value of mm1 and mm2 are different. And then we change the target function. And we change the target function as well for the mesh functions. And this time, let's run the plot again. Okay, you can see the contours change dramatically. And now we have two poles with the highest value or highest temperature. So in this time, we can also plot the values or the contour lines with respect to theta and phi for this new target function. We do the same thing, just to replace this part with the new target function. And all the code that outside this part are exactly the same. Okay, you can see this time the theta phi plane is totally changed. And we can use this one to compare with the surface we have here. They are completely different in the first case and in the second case. And also we can compare this one with the plot here. In this video, I have demonstrated two common functions that be useful for this type of visualization if the constraint is on sphere. One is the spherical plot 3D. So you can directly using x, y, z as a function for the function of mesh on the surface of this plot. And if you know how to parameterize x, y, z in terms of theta and phi, the other function, plot 3D, is really useful in this case. Hopefully you enjoy the content and see you next time.